Can you hear me? Online, can you hear me?
Yes.
Awesome, thank you. All right. right, welcome back. Right, well, let's settle down. All right, so let's get started on our second week. Yes. Oh. Video mute. Volume. Is that better? There. Let's do this, huh? Hello, hello. Let's see my laptop, DVD, video mute, front camera view, audio mute. Hello, hello. Is that better? You still hear it? Right over here? Everywhere? So this is off. Well, we'll see. Should be okay. Let's see. Right, so we are getting started on the second week. We should all have a working database. So we should have a working database. We get started with designing a database. We talked about UML and class diagrams as a language that we can all agree on how to represent the data that we are going to be building. So that could be understood regardless of whether you're coming from C#, Java, or you're a data analyst, you're a business analyst. It's graphical, it's easy to communicate. And the most important part is that it's a tool for communication, right, for documentation, and that it can be adapted depending on the audience, right? So that, if it is a data analyst you're going to be talking about, then it makes sense to reify a UML diagram to add, mapping tables and the foreign keys and the primary keys, fields that you would normally not include in a UML class diagram, but just because it makes it easier to converse with that particular audience, it makes sense to make those changes. Or if you're talking to folks that are object-oriented programming, using object-oriented programming languages, it might help to add arrays and data types that you would not normally capture in a UML class diagram, but makes the conversation much easier. And that we should feel comfortable moving between the different ways that we can represent data, depending on what it is that we're doing with that data. How is it that we're implementing it? Yes. So oftentimes you'll hear me, talk about classes as tables and tables as classes. Eventually, the distinction will blur, right? And it we'll be able to think about both of them at the same time, understanding that UML is just a visual language that just makes it easier to design tables. Yes. All right, and we should be able to go back and forth between these two. Okay. So yeah, so let's keep talking about UML. And we had just started. I do want to cover a little bit about the assignment again, especially the part where it's the challenge part, which you're not required to do. Undergrads are not required to do the challenge. Nevertheless, it drives home the challenge of bridging these two worlds, right? The relational world, which is fairly flat, right? You have flat records that you can't create hierarchies that need to reference each other using primary keys and foreign keys. So that flat world, and then how it maps to a much more modern technology such as object-oriented programming and component technology and aspect-oriented programming. So all these modern ideas are just not representable in relational databases. Yes. So I just want to drive that home a little further. So let's get back where we left off. First, any questions before we begin? Yes. It's more based on the lecture. It's going to be all most of it fill in the blanks and multiple choices. But yeah, no, everything that you've seen in the slides. Yes, right. Yep. And it's open book, so you can take a look at all the slides that are available to you. So be familiar where things are. If you want to just jump real quick at a definition or anything like that, where you'd be able to find it. Okay. Yes.
Are we doing this in class?
Yes, it is in class. The first couple of minutes of the I'll make it available. I think there's a password I need to give you to unlock the quiz. Yes.
The quiz content, is that all the way up through today's lecture, or was it ended last week's?
I don't remember. Yeah. Okay. Yes. The first quiz is designing the data, so it always covers the week before. Yeah. So it's designing the database. Yes. Yep. Yep. Okay. All right. So let's take a look at the material. Installing the database, designing. We talked about that. All right. So let me cover a couple of topics that just let's review where we left off. Right. So we had talked about that we wanted to be able to straddle between these different worlds, right? The English, very inconsistent, very contradictory, very vague understanding of the data as described by human language, and then its formal representation, either using some visual language such as UML or some more formal programmatic language such as SQL, and then other formal representations in any number of programming languages, right? And we need to be able to jump between these worlds back and forth. Eventually, in our minds, that we could blend them, right? That we can think and design here, but always understanding that we need to convert it into this more formal representation. Yes. So we talked about that. We talked about an algorithm. We talked about an algorithm that would allow us to convert between class diagrams and relational model, and from relational model back to the class diagrams. We came up with a really simple algorithm that, given a relational schema, meaning giving a table with primary keys, foreign keys, and fields of their data types and whatnot, that we could create a equivalent class diagram following this very simple algorithm, right? So for every class, we create a class for every table. We create for every foreign key, we're going to have a star, right? The asterisk on the weak side, and a 1 on the strong side, right? And so we tried it out, right, with this simple example of starting off with tables: student, department, course, section, and enrollment with these fields. And if you apply this algorithm, you end up with this class diagram, right? We then have the inverse transformation, right, where we can start instead from a class diagram and you can generate the equivalent relational model, right? So starting off with a UML class diagram, and you end up with tables. So kind of like the inverse transformation, right, where you start off with a class diagram like we just saw earlier, so like classes of a student, department, course, section, enrollment, and then if you apply this algorithm, where you're going to create one table for every class, wherever you have the weak side, the star, you put a foreign key. Wherever you see the strong side, that's a primary key, right? And so if you apply this algorithm to this class diagram, you end up with this table, right? With these set of tables. So one can imagine that you could generate a program that does this for you, right? That you come up with a set of classes. If you apply this algorithm, you push a button, and it generates for you this code. Actually, these tools already exist. They're fairly expensive, but they're out there. Rational rows is one of them. IBM bought it a couple of years ago, and it can do forwards and reverse engineering. You can give it Java, generates SQL, generates UML, generates any language you want, right? And it can transform between them because it is equivalent, obviously. We'll see that there are actually a few limitations, right? That you can't transform everything, right? Because there are certain things that just don't have an equivalence in some of these languages. So anyway, once you have this resulting schema, you could go a little further and make some decisions to convert the resulting schema to be a little more down to earth, right? That the schema that's generated is a little bit too generic, right? And it makes certain assumptions that are not necessarily true. So for instance, by default, our algorithm, it chooses an artificial key as its primary key. Yes, that's fine, right? But it's kind of a lazy, it's a lazy decision, right? Just like somebody made the decision that we all have student ID or faculty ID or employee ID. Yes, just because they couldn't think of something that made us unique enough in the organization, they just said, "Oh, forget it. Everybody's going to have a faculty ID or student ID. So my first name, last name, and whatnot wasn't enough to make me unique." Yes, so they had to come up with this artificial key. Yes, same thing as here. We came up with this artificial key, but to ground it on, one might choose that instead of choosing this artificial key, one might say, well, you know what, the department names are unique enough. Yes, if you can guarantee that the department names are unique within the university, then there's no point on having two things that are unique, right? We can just eliminate the primary key and choose the department name as a unique key. Make sense? Whenever possible, if it is possible, we would, if we have the choice, right, we would always choose a field that is already unique, right? So for instance, you might, today, if you're going to create an account, oftentimes they allow you to use your email, right, as a unique identifier, right? So instead of having a primary key, they use the email, presumably it's unique inside, within the world, right? And so they can use as the primary key. So that's the case here. Now, because we changed this, we know that there's a whole bunch of other tables that reference that department ID, right? So instead of using that the artificial key, right, we would replace it with the name of the department. Yes, we have to go back and change all the other tables. Other things such as also some rules that we might know of. For instance, you might know that if you're a student or faculty and you're going to park in the university, you need a permit, and that permit usually is tied to one person, right? You can't share it, and so for instance, that the rule is that there's a one-to-one relationship, right? If there's a record for a student, there might be a record for a permit, and that permit is only for that one student. There's a one-to-one relationship. Yes. So if you know that, then you know that this student ID over here, that is the foreign key that references the student, is already unique, right? It's already referencing the student that permit belongs to. So the fact that you have this additional artificial key as a primary key is really not needed, right? We could just use the student ID already is unique, right, as not only the foreign key that points to the student, but also as the primary key of the whole record. Make sense, right? You might decide to do that, right? Other things that as we go along, for instance, the enrollment table that our algorithm came up with was this enrollment table, right? It has a primary key, the EID for the enrollment. It had two foreign keys, one to the student, one to the section, right? Because there's the enrollment associates a student with a section, right? It says that student is enrolled in that section. So it has two foreign keys, one to the section, one to the student. Yes, right? So that's the equivalent table that our algorithm came up with, right? The primary key, again, an artificial key, and then the two foreign keys, and then the grade, right? What grade they got in that section. Well, now the problem with this implementation is that, for instance, if student Alice, right, enrolls in databases, okay, and the primary key is, say, 1, 2, 3, I could insert another record, right, whose ID is unique, maybe 2, 3, 4 or something, yes. But again, repeat the fact that Alice is again enrolled in databases, right? So I'm saying twice that Alice is and the same student is enrolled in the same section twice, which makes no sense, right? And usually, there might be some requirement in the in the requirements document that says clearly that a student cannot be enrolled in the same section twice, right? Okay, so this implementation right here, you might look at it and says, well, it's okay. I mean, it's not going to happen. It's very rare that would actually happen, right? But nevertheless, notice that this implementation would allow us to break that rule, right? The business rule. So how could we fix this? Well, one way to fix this is that right, instead of using the artificial key for the enrollment table, we could take both the foreign keys, right, and combine them, right, put them in curly brackets, and say that together, the student section and the section ID together, the combination of those two is unique, right? Meaning there can't be another record that has exactly the same student ID and the same section ID, right? And that's called a compound primary key. So it is a primary key, makes the record unique, and it's enforcing the rule. See that? It's enforcing the rule that no, I'm not going to allow any other record that has the same student ID and the same section, right? The database will not allow it. Make sense? Yes. Yep. Yeah, it would literally be the comma, right? You would say primary key and then the field, comma, the field. And you would declare each foreign key independently. So you say, student ID, foreign key, student ID, references, table, blah, 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 student dot, student ID, and then another foreign key, right? And declare the section ID, also referencing the section dot section ID. But then when you declare the primary key, you would say, student ID, comma, section ID, or the combination of the two. Yeah, we haven't seen that syntax. Right now, you can declare just a single primary key, say primary key, and then parentheses the primary key. Well, you can alter and you can put a comma after that and list any number of fields that together make up the primary key. And the enforcement is that the combination of the two has to be unique. Yep. So going further, same thing like we remember we had modified the department to be the department name instead of the department ID. Yeah. Also, we could say the same thing about the course. Instead of if we can guarantee that the titles are unique, right? That there's only one cs3200 database design, right? There's no other course named that way, right? Same thing. We can make the decision that it is irrelevant to have the primary key, an artificial key such as CID. Instead, we could just use the title as the primary key. Make sense? What else? Yeah. So the conclusion from last class basically was that if you want to design good databases, you start at the UML level, at the conceptual level, right? At the graphical visual level, you do the design, then you have an output, a relational database. And if you want to make any changes, maybe to an existing database, then what you should do is first convert that relational database into its equivalent visual UML diagram, make your changes there, and then convert back into the relational world. Make sense? Obviously, some people can do this in their heads, right? They look at tables and immediately they're thinking in classes. Yes, they're already are able to live in both worlds at the same time. So here's an example of taking the description of the university as composed of multiple departments and offering a whole bunch of courses. So this might be the result of having interviewed a dean, right? Or having interviewed faculty and blah, blah, blah. So students, they graduate every year. They have in a particular major, they enroll in a whole bunch of courses. They have a whole bunch of sections. And they might ramble on, right, talking about things that are completely irrelevant to what we're building. And after these interviews, the the interviewers, the engineers, us, right, go back and try to gather all these things and organize what we've witnessed, right, this interview, and we start looking for verbs and nouns and things that give us an idea of what it is that we're building, right? And the nouns here, we're going to come up with some kind of vocabulary where we make sure that the nouns are what that we understand what every noun means, or that there aren't 2 or 3 different nouns that refer to the same thing, right? Are they aliases of the same thing? And we come up with an official list of terms, right? An official list of nouns, and it's the same language that we're all going to use to talk about when we build this project. Yes, same thing with the verbs or verb phrases, and so nouns are going to drive the classes that we're going to build, right? Either classes or attributes of classes. Yes, whereas the verb phrases are going to establish the relationships between those nouns, right, and those classes, right? So these are going to define the boxes in the UML class diagram, and these are going to define the lines that connect the different classes. Yes. Now we have to be careful because oftentimes, most verb phrases, we think that most of them are binary. They're relating just 2 nouns, but actually we have to be careful because some verb phrases might actually be referring to 3 different nouns or 4 different nouns, right? And creating relationships that are not just binary, but they're tertiary or more than 3 classes. So let's take a look at what we might do. Now, always have to be careful in these interviews. Again, folks might ramble on and talk about things that are irrelevant and actually completely skip over things that are very relevant, right? So it is our job as interviewers or engineers to help out the process, right, of identifying what it is that we're building. So once we have all these nouns and verbs, we come up with a preliminary class diagram, such as this one, right? And so all these nouns, presumably you might have one class for every noun that you might have identified in the list of nouns. Yes, and the verbs connect the different nouns. Now this is a very preliminary class diagram that still has to be vetted out, right? It has to go through a process, that iterative process, right, of identifying things, relationships that are not adequate or relationships that are redundant. Okay. That maybe a class shouldn't be a class at all, that it should be an attribute of something else. Okay, so it has to go through a process of iteratively pruning this, looking for redundancies, looking for inappropriate relationships and things like that. Okay, so this is just a preliminary. So let's try and relate to take a look at some of these relationships. So let's look for inadequate relationships. Okay, so what we mean by that is that we measure whether we measure whether this is good or not, right? We measure the value of this based on, again, always the requirements. Always go back to the requirements, right? The requirements, the use cases, right? That we talked about last week. What those are the use cases list the goals of the users. The users in the use cases, right? Folks might have listed, hey, I want to list all the sections that a student is enrolled in, right? I want to, given a section, I want to list all the students and faculty and TAs that are in that section. Given a student, I would like to report on their grades, throughout the last semester, blah, 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 blah. So all those are the use cases, yes, which eventually are going to translate to some kind of select statement, right? Select student where table, blah, 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 yeah, okay. So those requirements, you need to measure the value of this class diagram based on those requirements, right? Can I ask it these questions? Does my database support a query? Yes, right? So you take your query and says, okay, if I have this query, the query is, I want to see which professor is advising which student. Well, no, there's no table here or class that captures that. Yes, or the question might be, can this answer me students that used to be in a department and they changed careers? Well, no, there's no audit here. There's no history of what the student is doing. Yes, Okay. So or if you ask, okay, does this answer me which grades did a professor give a student for a particular section? Well, yeah, apparently it does, right? Because it's kind of relationship here of professors, sections, grades, and students. Yes. Right. So whether this is a valuable class diagram or not is based on the kind of questions you're going to give it. Yes. Right. So for instance, let's take a look at this relationship. Right. Somebody might have read in the requirements, might have read students enroll in courses. Yes. I think that there was a sentence like that in the requirements, right? And there was another sentence saying that courses have many sections. Yes. Now, if you literally read that in English, you might come up with this class diagram. Students enrolls in courses, and notice that there's a many-to-many relationship. Yes, right. One student is enrolled in many courses, but one course has many students enrolled in it. That looks okay. Yes, and then later on in the sentence it says that one course has many sections, so that looks fine as well. Okay. The problem is that if you measure this against the question, say you go to Canvas and you want a list of all the courses that you're enrolled in, right? Okay. Or vice versa. If I go into I go into Canvas and I want to see a list of all the students enrolled in this section, right? This will not be able to answer that question, right? Because actually what you enroll in is not on a course. You actually enroll in a section, not a course, right? So this class diagram will not be able to answer you, which section are you enrolled in, right? If I want to be able to say, well, give me a section, the section I'm teaching section 4 and some other professors teaching section 3. If I go to my Canvas, I get a list of students, which is a different list of students from some other section. Yes. So this is not able to answer this question, because notice that the student knows about the course but has no relationship whatsoever with the section. There's no joining of these tables, right, that would allow me to filter which sections are for a particular student, right, or what are the students for a given section. See that? Right. I might be able to tell you what are all the students in a particular course, but I can't break them out by section. See that? Right. So actually this is not the implementation that I would want. Actually, this is actually meant to be the other way around. Right? Students enroll in sections, right? And then courses do have many sections. Make sense? Right, so you always have to measure the validity of a class diagram based on the queries that you're going to ask it. Okay. So we have to do that for every path. We have to look at our class diagram, look at the kind of questions we're going to ask it, and ask ourselves, okay, can we answer the questions given this class diagram? Okay. And it has to be done exhaustively. Let's look at other things. A couple more. Here we have, student receives a grade, yes, or professor assigns grade. All right. Okay. Now, and that looks okay. The problem is that here, the student is going to have what? A collection of grades, A's, B's, and C's, and whatnot. Yes, hopefully mostly A's. But notice that the student won't be able to tell what did I get for which grade did I get for what section. Right? Did I get this A for databases or web dev or what? For what did I get these grades? I just have these grades. I can calculate your grade point average. I just won't know which grade goes with what section. See that? Because notice that the grade has absolutely no relationship to the section. There's no way to say, oh, you got this student got this particular grade for that particular section. See that? So there's something missing in there. Same thing for the professor. When the professor assigns the grade, again, we don't know for what section are you talking about, because the professor could be teaching multiple sections. Which one is it? Yes. So again, the measure is what is it that we can answer or we can't answer. And usually these problems arise because when we read it in English, right, we usually tend to combine nouns in pairs, right? When actually, in fact, some verb phrases might combine, three nouns or 4 nouns, right, where they are somehow all related. So we might have read lazily, student receives grades, and we might have stopped at that. But actually, the full sentence might have read something like student receives a grade for an enrolled section, right? So now we realize that it's a three-way relationship as opposed to a two-way relationship, right? Same thing with professor assigns a grade. It's actually of the verb phrase. It's a professor assigns a grade for a student for their particular section. So if you reread the sentence, you realize that instead of being student receives a grade, it's actually a three-way relationship, right? A student, section, and a grade, right? Now in UML, it's easy to capture. It's just not. So it's good. There's a three-way relationship. For any one combination of a student and section, there is one grade, right? So if you give me a different combination of sections and student, it'll be a different grade, okay? Now we can't implement this in SQL, right? This is very abstract. This is very. We need to make it concrete. We need to reify this, right, and convert it into something equivalent that we can implement it in SQL. So what we're going to do is we're going to replace this three-way relationship with an additional class, right? An additional class that is going to have foreign keys that point to the student, point to the section, and point to the grade. See that? Right? Okay. And so now this we can implement, right? We can go back to our original class diagram and fix it. Right? We can fix it, right? And remove the grade, which was not enough, right? And replace it here with something that relates all these things, right? Grades and sections and receives. Actually, the grade is going to be brought into the table as a field, right? As opposed to instead of a separate record. Does that make sense? Yep. Yes.
If grade is going to come into the grade assignment as a field, why do you have a separate box then for grade?
Yeah, eventually there's a whole section on asking about grade, professor, year, car model. Should they even be a separate class, right? And that's part of the conversion. Yep. Also, we need to consider about redundant relationships, and what we mean by that. Oh, that's mine. Redundant relationships, and what we mean by that is that if you have a question for a database, is there more than one way that you can answer it, right? And there shouldn't be, right? If you can answer a query in a database in two different ways, that means there's a redundancy in the database, okay? And you should eliminate it, right? Remember the example I gave earlier. If you have two watches, and logically they would have to have the same value, but for any whatever reason, at some point they deviate, right? You devalue the the trust in any one of the two sources of information, right? So it's better to have just one source, and that is correct than two that you can't trust. So for instance, we need to consider different paths of the data paths to see if there are redundancies. And in particular, there is a redundancy in being able to, when you're going to answer the question, I want to know all the sections a student is enrolled in. That's a very common question, right? Give me a student, give me all the students that they're enrolled in. Yes. And given the current class diagram, we can actually answer two ways: either going through the enrollments, okay, or going through the sections, right? Starting at the grade assignment. So let's take a look at that. Right. So because right now we have this assigns, right? We can join assigns with professor and sections, and have the information if you go to grades, sections, and professor. So whenever you have a cycle like this, whenever you have a cycle like that, right, it's always suspect, right? It's always a red flag should come up, right? That I can traverse the map, I can traverse these paths in different ways. Yes. Okay. So if it allows me to navigate in two different ways, you should always say, "Oop, maybe there's a possible redundancy here," right? Can I eliminate it? Like for instance, here we can eliminate this professor, right? We can eliminate this path. We had said that the grade was given by a particular professor. They would say that, right? That's why we had the foreign key to the professor. But if we, for instance, additionally know that a particular section is taught by a single professor, yes, then this relationship of the section referencing the professor, it's actually enough, right? It's kind of redundant saying that the grade is given by professor, but there's only one professor for a given section. There's no need to have this additional line here. You already know that there's one professor for that section, so we can reasonably just remove that from remove the redundancy by removing that reference there. Make sense? So again, this has to be done for every path. You have to follow all the different paths and look for any redundancies, and you remove them. Now, some things that are cycles are not necessarily redundant. Okay, so here's a cycle of going from departments to students to grade assignments, sections, and courses, and then back to the department. So that's definitely a cycle, and you should consider it and take a look at it. Now, it depends what you're asking, right? If the question is, can I list all the students in a particular major, right? Then definitely I could do it by departments and students, right? That list line over here tells me that for a given department, these are all the students. Yes. And you might ask, well, can I answer the same question if I go this long route, right? This green path, okay? And after joining all these tables, you'll find out that no, you can't, right? You can give me all the students, but you can't break them out by department, right? You'll end up with a whole bunch of students, but you won't know which department they belong to. Yes. That too. Yep. That too. Exactly. Yep. Exactly. So yeah. But it also depends on the question, right? It could be that the question is, well, give me a list of all the students, and then these would be redundant, right? Because they both can answer, give me a list of all the students across all departments, right? So then you would have to deal with it. Well, okay, now there's a redundancy here. Yes. Well, you could have department courses in different departments as well. They're not in the same department. Mm-hmm. Yes. Yep. Right. Yep. So depending on the question, something might be or might not be redundant. So, and if you change the question, then something might be redundant or not, right? So given the question of answering that question, then we would leave both of them, and we don't need to remove any path here. Okay. Right. So removing all these paths that we have identified either as redundant or as redundant or inadequate, right? We end up with something a little more simpler, which we have the grade assignments, sections, and whatnot, right? Okay, so our algorithm did have a couple limitations that we mentioned earlier. For instance, it does not deal with many-to-many, right? It only deals with one-to-manys, right? So let's explore that just a little bit. For instance, you might change the requirements that a student might not only can they enroll in one department, they could have double majors, right? Or a minor and a major. Okay, so you would capture something like this, where you have a many-to-many instead of just a one-to-many. If that's the case, we would have to reify it, right? Add an additional class that does the mapping between the students and the majors, right? Right. So that's easy. But let's say, how does that spread across the rest of the diagram? Say you're capturing a GPA, right? Say you're capturing a GPA. Now, if you're only allowed to be in one department, then the GPA could be just related to the student. There's only one GPA that you could possibly have. So it could be associated to the student. That's fine. Yes. Okay. Now, if you do choose a request that you can be in different, you can major in multiple departments. Now the class diagram fails. Okay. So what used to be fine before is no longer fine now, right? Because one thing that we might do is say, okay, well, now because you have multiple majors, I'm going to allow you to have multiple GPAs. Yes, right? But notice that this particular GPA are all associated to the student, but there's no way for you to map and say that that particular GPA is for a particular department. No way for you to distinguish, for you know that they both belong to the students, but there's no way for you to say, well, which GPA belongs to which department. Make sense? Okay. So yes, I have a place to store multiple GPAs, but I don't know for which department. So what used to work in a previous implementation doesn't work in a second in this implementation, right? So we need to be able to move things around now. We have to now say that the GPA has to be related to the department. This GPA is not only is related to the student, but is also related to the department. So now what it used to be a binary relationship is now a three-way relationship, right? Between student, department, and major, right? As always, right? That's totally fine in UML, right? Having a three-way relationship with lines and a dot in the middle, that's totally fine in UML. But when you're actually going to implement it in relational model, you have to convert it into something equivalent that can actually be implemented. So that's why we reify this relationship right here and convert it into an equivalent class here that has the three-way relationships, right? So instead of one many-to-many, we're going to have several one-to-manys. Yes. Okay, and which obviously it's going to be implemented in a relational model as this having three foreign keys: one to the department, one to the student, and one to the major. Right? Yes. Yeah, so what changes do I need to my class diagram so that I can actually implement this in the relational model, right?
So, let's say when we do the stuff, should we do the reifying person, or should we do like a general?
Yeah, so for the one-to-many, you can leave it, right? But many-to-many, it needs to be reified. Yep. Yeah. So what else? How about if we consider that students might be unregistered, right? They have undeclared, right? So they might not even be associated to a department at all. Okay. So this relation now becomes optional. So there is a student record, yes, but there might be no relationship to any department yet, right? Maybe the first semester or at the end of the second semester, they have to register and say which department. But meanwhile, right, they could be a student record, but no relationship with the department. Okay. So what do you do with the GPA, right? How do you capture that? And so one appropriate way to capture is that there shouldn't be any GPA relationship until you decide whether you are actually registered. If you are registered, and then there is a record that says what department you belong to and a associated GPA that goes along with that, right? And here's where you capture the fact that it's optional, right? Maybe there's a record, maybe there's no record at all, right? Okay. Okay, so here's then there's also a converting classes that maybe are not necessary, right? So for instance, the fact that you're capturing the letter, grade A, B, C, and whatnot, right? Perhaps this shouldn't be just a whole class on its own. It could just be an attribute of the grade assignment, right? Or the year, right? Instead of being its own table or its own class, perhaps it could just be an attribute of the student, or it could be maybe an attribute of the section, right? The section that was when was that section offered, right? Or same thing with the permits, right? The license plate and the car model, perhaps, right? There's no need to have an entire table for that. They could just be varchar fields or string fields, part of the permit. Yes. Again, these are all decisions. Or, depending on how much information we're capturing for the professor, say we're only capturing the username, right? If we're capturing the username, then do I need an entire table for the professor? Right, professors are not that important, so maybe this just the username could be just just sucked into the section table, right? Just as one field. Now, instead of if the requirements are that we capture a lot of information about faculty, right? We capture their office hours, where their office is, their contact information, whether they're tenured or not, or whatever, right? Then obviously an attribute is not enough, right? It can't be a field in some class. It needs to be its own class. Make sense? Right? Again, those decisions of whether it's a class, an attribute, how do we split it, blah, blah, blah. That's the database design, which is the title of this course, right? So that's the process of deciding which way you're going to split it or not. Classes, yeah. So this is a simple algorithm of doing that. So once you do that and split up the year, the grade, the professor, the permits and whatnot, you end up with, guess what? The original class that we started off with, right? All this work and concluding that the original class diagram that we had at the beginning was the perfect design. Other things might be that in the throughout our process of designing, the interviewers, the interviewee, that all the requirements that we wrote, left out a whole bunch of stuff, right? They rambled on a whole bunch of things that was irrelevant, and they completely skipped over things that were relevant. Yes, perhaps they assumed that we knew certain things, so they just left it out. Like for instance, they might have not said that students have first names and last names and middle names and blah blah blah, right? Or social security numbers. Probably because they assume that we know that all human beings or U.S. citizens have certain attributes. Yes, so they leave those things out. So for instance, they might have told us that students have a graduation year, but they have not told us that they have a username, a password, first name. Those are assumed, right? We're assuming that they have all these traits, all these features. So we would fill this in. We would fill in all the attributes and fields that were left not unset, right? And we would go back to them and obviously make sure that this is what they meant. And we would add, titles for the courses, the name of the departments, right? The names and whatnot. Okay. Yeah, cardinality, blah, blah, blah. Okay. Did we talk about aggregation and composition? We met last time. I forget. No. Yeah. Let's talk about it real quick. So aggregation and composition, we might want to, in addition, whenever we're capturing a one-to-many relationship, one of the things that we might want to capture, it depends, right? As a design decision, we might want to capture whether there is a life cycle dependency between the records. Okay, if I have a record that is associated to multiple records, right? What happens if I remove one of them? What happens to the other ones, right? So, for instance, if I have a whole bunch of products, right, and in the table of products, and they're all a whole bunch of records, yes, and then an order comes in. An order comes in, and the order says, well, I want 2 of those, 3 of these, and 5 of those. Yes, and that's my order. My order has 3 entries, right? And it says I want, and these are the ones that I want. Yes, and they have foreign keys pointing to the products. Yes. Now, what happens if I remove the product? Somebody cancels the product and it gets removed from the database. What should happen to the products? Nothing, right? The product should stay. So we say that the relationship between orders and products is an aggregation. Okay, one of them has references to the other, but if one of them dies, the other ones stay. Make sense? Okay, so we say there's an aggregation relationship, and the way we capture that is by an open diamond, right, on the one side, right, on the strong side. Okay, so a car has many wheels. If the record for the car goes away, do I still have the wheels? Probably I do, right, that I can use in another car. This example is a little more gruesome. Composition is that you want to capture the fact that if you have, again, a one-to-many relationship between one record and multiple records, if you remove one of the records, what happens to the other ones, right? If I say that if the existence of one depends on the existence of the other, then we say that's a composition. Okay. So here's a gruesome example. We have a person that has hands and legs. If I remove the person, well, also all the other records go away as well, right? We want to cascade. We want to cascade the removal of one record. We want to cascade that removal to all the other records. Make sense? It propagates the deletion. So we say composition. Now notice that both composition and aggregation are only used for one-to-many relationships, right? So a one-to-many relationship where you have one and star, right? Okay, that's where you would either decide to document whether it's a composition, aggregation, or you might leave it alone. You might not even put the diamond. Yes. So you're leaving it up to the engineer who's implementing this, right, to decide whether it's a composition or an aggregation. Generalization is another type of a relationship where you declare a base class, and then you have derived classes where the base class defines fields that are common to both of them, right? And then you have the other ones are special cases, such as you might have an employee, and then you might have different types of employees, right? So the salaried employee, full-time employee, hourly employee, and each one has ways that that you would calculate, for instance, their salary, right? So they both have different properties that are specific to them, right? Anyway, I do want to capture this and talk about it as part of the assignment. Let's see. Okay. Continue. Oh, this module was supposed to open up on its own, and it didn't. Were you not able to see week 3? You weren't able to see it? Okay. Okay. Let's talk about data definition. So we talked about designing, and the process of designing is coming up with what's going to be the schema, right? And largely entails on coming up with what is the class diagram that we're going to be building. But eventually that class diagram needs to be converted into an equivalent set of tables. Yes. Okay. And so let's talk about that. Sure. So what are tables? So tables, now tables, when SQL was first came out, and they were trying to describe what a database is and how to interact with databases, they all started with sets, right? Set theory, and table is kind of like an abstraction of the idea of a set, right? And where a set has a whole bunch of items that belong to that set, right? Equivalently, we think about it in the same way as a table. So a table is a collection of rows, where each row is a data point, right? And each data point can have all sorts of attributes. Yes. Okay. So likewise, right? You'll hear me say multiple times, right? The equivalence of a table and a set, and then the rows in a table and the data points, items instead of a set. Okay. And then the operations that you can do on tables, whether you find records that are in a table related to other records that in some other table, right? Those operations come straight from set theory, right? Where you do joining and differences and unions of sets. Yes, right? So the same operations that we'll see that we apply on tables come straight from set theory. Okay, so you'll hear me say back and forth, right? Making this analogy, right? So yeah, so tables is just one way. It's just an abstraction of how we're going to think about how the data is organized. Okay, and so tables are just going to have a whole bunch of rows and columns. Each column represents a different field in each one of these records. So for instance, if you have the schema, the same schema that we've been using so far, right? Students, departments, course, sections, so on and so forth, right? We might have the following set of tables, right? Where you have a list of students, Joe, Dean, and whatnot, graduation year. Right? You have the list of departments, the list of enrollments, right? The sections, the courses, right? And the way they're related to one another, right, is through the use of foreign keys and primary keys, right? So the department has primary keys 1, 2, 3, and 2, 3, 4, and the way that the relationship works is that the students know which department they belong to because they have a field which is a foreign key referencing the department. right? And then here we have a mapping table, the enrollment mapping table, which is mapping students, saying that these students are enrolled in these sections over here. Yeah. Okay. Notice that the fields in the class diagram. Well, I don't have the class diagram, but in the class diagram, we didn't have any foreign keys and primary keys, right? We only had the real fields, these fields, right? The names, the graduation year, right? The grades, right? The professors, the years offered, but everything else, section IDs and course IDs, the primary keys and foreign keys and things like that, right? Those are specific to the relational model. It is because they exist only because that is the only way in relational model that you can implement the relationships between records. Yes, right. It's an artifact of the fact that that's how SQL stores things in relates records. Make sense? Right. These are not fields that really are part of the meaning of whatever it is that you're describing. Right. There's just an artifact of the fact that we're using relational model. So let's talk about normalizing data. So when we talk about normalizing data, it usually entails the splitting up of large data sets. Okay, because you might say, hey, why are we having all these tables? Why do we have these 5, 6, 7 different tables? Why can't everything just live all in one single place? Yes, right. Why are we splitting up into multiple? Why can't I have just one table where I have everything? Yeah, I can have the students over here, right, and show them what courses they're in, right, and the professors that's teaching that section and what it was offered and the grade you got, right. So if we put everything in one table, you'll notice, okay, we see that Joe and Alice and Bob and Dan, they all went through chemistry, right. They're all in the chemistry department. Right, they're all taking the same course, calculus, right? Taught by the same professor. So we'll start seeing that the same piece of text, the same piece of information is being repeated over and over and over. You see this, right? When you do this and put together all the data in one single place, you find yourself just repeating yourself: chemistry, 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 right? Math and math, 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 a whole bunch of places, right? So it's kind of the example that I mentioned earlier. If you say you're making a poll and in your questionnaire you're asking part of your questions is where your address or something like that, right? Or the town or whatnot, and if you find out a family of 5 and you're asking each one of them the same questions, you end up that you capture the address 5 times. Yes, and so what's the problem with that? I don't see any problem with that. Well, the problem is that, say you mistype the address, right? Maybe some of them you say you live in Adams Street, where the other one you list them as Adams. You put an S at the end. Yes. So if you do a query of where do they live, it might come up with only 3 people living there, right? Or 2, right? 3 live in one Adam and the other one live in Adams. So whenever you have this redundancy of capturing the information multiple times, it is very, very easy to introduce inconsistent data, right? I might misspell it. Instead of a Y, I might use an I, or over here I might forget the H, and it all of a sudden, and now these 4 students are supposed to be in the same department, but actually they live in 2 or 3 different departments. See that? Right. So the way we fix that is by splitting it. Instead of capturing chemistry department 4 times, we create a separate table for the chemistry department. Make sense? Right, where the chemistry is captured only 1 record. Right. So the act of going from one big table into multiple smaller tables, is what we call normalization, to normalize the database. Make sense? Right. And the reason we do that is to remove redundancy, remove inconsistency. So how do we create these tables? Let's create our first table. We're creating the student table, right? So this is the SQL query that we would use. Right? We create table student, right? The command is called create table. Then the name of the table, which is not following my naming convention. It's supposed to be a noun. Yes, it is a noun, but it's supposed to be plural, which is not plural. And then parentheses, and then the names of the fields, right? SID, SName, right? Followed by their data type, int, varchar, the size of how much varchar it is. Whether it's required or not null means that it cannot be null, meaning you have to give me this value. If you try to insert data and you don't give me this value, I will complain, right? And the database will not let you insert that information. Yes. Also notice here, we haven't said that we haven't said anything about SID or any of these being unique. Right? So it would be totally fine having two records with the same ID, with the same name. It's totally fine. SQL will not stop you, right? Inserting redundant data, right? Later on, we'll see, additional syntax for being able to, not allow that, right? All right, so let's talk about null values. So null values, null, as it says here, it means that we don't know the value. It doesn't mean that it's blank, right? It doesn't mean that it's 0 or -1 or the empty string. It means that we have no value, right? And once you have no value, then it means that you can't make any decisions of that value. You can't know if it's bigger, if it's smaller, if it's you can't say. So it will not participate in any query. Right? If a field is null, it will not participate in any select statement that you might throw at it. Right? So oftentimes, you do a real query, and then all of a sudden it comes up to you, oh, there's 300 records, and you were expecting 3,000. So what happened to my other 2,700 records? Where are they? It's probably because, right, the particular field that you use in your query was null, right, and it's not participating in your query. So yeah, null means I don't know the value. It's as if somebody left a question unanswered, right? I don't know. What is the answer correct? I don't know. I don't have an answer for it. Let's talk about keys. So keys, by keys we mean the you have any number of fields, right? Any number of fields, and but some fields are special. Well, you're going to treat them differently, okay? And so usually we want to identify a specific set of fields that make a record unique. Yes, right? So for instance, we might choose that the last name in a room this small, maybe the last name is enough to be unique. Maybe not. I don't know. Probably we have several folks with the same last name. I don't know, right? So we might decide that maybe last name is not enough, right? So we might say, well, the combination of first name and last name perhaps is enough to make you unique in this room. Yes, right? And say it's true. Say it's true that first name and last name make us unique. Okay. Say somebody says, well, let's add the middle initial in there. Okay. Does that make you any more unique? It doesn't, right? So first name and last name, if first name and last name is enough to make you unique within a particular context, then adding another field doesn't make you any more unique. Make sense? So we want to distinguish we want to find out what is the minimum set of fields, right? The minimum set of columns that make a particular record unique. Make sense? Right? So we say that a super key, there's keys and super keys, right, is a set of fields that might contain fields in there that are superfluous. So for instance, we say that if we take the first name and last name, make it unique enough, and we add the middle initial, right? The middle initial is superfluous, right? I don't need it to make you more unique. So we say that first, middle, and last name is a super key that contains the key, which is first name and last name. Make sense? Right? Just jargon, just database jargon. Yeah, so a super key might contain a superfluous key. So how is it that we choose the keys, right? We want to be able to choose keys with, again, the intention is that we want it to make you unique, right? Sometimes we choose the keys to enforce a rule. Yes, No, well, we're trying to decide when we're choosing the primary key, which keys do we use, right? And so the question is, are these two fields enough to be the primary key, or do I need a third one, right? And so which comes to the question that I was making, right? Of saying, well, maybe I don't need all three to make the primary key. Maybe I can ignore this third one and only do it with two, right? So a primary key is whatever you want it to be, right? So we're studying here how would we choose whether we use 2 or 3 or 4 keys, right? For deciding that. Yes.
Does a super key always have a key field?
Had what? I'm sorry. Yeah, right. So a super key. Well, the super key can also be the key if it has no superfluous fields.
Okay, so
Yeah.
like sometimes it has some-
Yes. Right. Yep. So sometimes we might choose the keys in order to enforce a rule, like before, right? We for instance, we chose the keys to be the combination of student ID and section ID, right? And we did that because we were trying to also enforce the rule that the combination of the two has to be unique, right? So that folks cannot enroll in the same section twice, right? So all these kinds of decisions, all these kinds of rules inform us on what to choose for our primary keys or the keys that we're going to be using. Okay. So depending on the rules, we might choose different keys. So for instance, if the rule is that a professor can teach a course, just once a year, maybe there's a rule like that, right? The university arbitrarily says, yeah, no, you can teach that course just once a year. That's it, just one semester, and you're done, right? Okay, well, how do you enforce that? Okay, well, we might choose that the primary key could be the combination of professor and the year that is offered. That combination has to be unique. If it's the same professor and the same year, nope, sorry, there's only one of those, one record. I cannot have another record with the same professor, the same year. Yes? So that key enforces, that primary key enforces that rule. Or that that course can only be taught a particular only once a year, right? So course, the combination of courses and year, and the year was offered. Okay, so this is the point I'm trying to make is that not only whether makes the record unique, but it's also because we might want to enforce certain business rules. Okay, and it might be that you choose a key, a primary key today, and as requirements change over time, right? Any particular choice of primary keys that you might have done in the past might not now be valid, right? Because new rules come up, right? New requirements come up in the university, and we need to enforce those rules, right? So we might have to go back and change the schema, right, to apply these rules. So, for instance, it is just an example of certain rules, certain records that break one of the rules. It violates number one, right? We have 2 different courses, and the professor is teaching in the same year, right? So that violates number one. Or this one, right, where you have the same course taught in the same year, it violates number 2, right? This one, the combination of professor, course, and year that was offered violates number 3, right? So you have to decide which primary keys, collection of primary keys, we're going to use to enforce certain rules. Duplicate records. So one of the reasons why we use primary keys is that we want to avoid databases to having duplicate records, right? Values that are the same exact from one record to another record. Now, databases don't stop you from introducing duplicate records, right? By default, right? If you create a table and you don't declare any primary keys, right? If you don't do that, which you don't have to, database doesn't stop you. It'd be perfectly fine introducing a record that has exactly the same values of another record. Yes. So you can have 10 records that have exactly the same values, and the database can't distinguish between them. They're identical as far as logically they're concerned. They're all identical, and there's no way for the database to distinguish one record from another. So if you delete one record, then you're going to delete all 4 of them, right? Or if you are updating one of them, they're all going to be updated, right? Because as far as the database is concerned, they're all identical, and they're all treat it as if it were one. So just be careful, right? The conclusion is that we should always add the constraint that records should be unique, right? And the way we do that is typically by using primary keys. Okay. So a primary key is an example of a constraint, right? Which you're saying, well, before this field, it's fine. It's not constrained. You could have values that repeat, right? By adding a constraint on that field and saying that it's primary key, then you're adding a constraint saying that no, sorry, the values in that field have to be unique, one record to the other, right? Plus other things that we'll see. Not only does it have to be unique, it also has what we're going to say. It's going to enforce referential integrity, and we'll talk that in a minute. Yeah, so primary keys also are used not only for uniqueness, but also because it allows the record to participate in references, right? And the way we do that is by using the keyword primary key and then the field that we want to be the key, right? In parentheses. And this could be just a more than one. We say DID comma field. So it could be a compound key as well, right? But in general, we're going to be using this simple syntax where we're declaring just this particular department ID as the primary key. Make sense? All right, so let's talk about foreign keys. So foreign keys is the counterpart of the primary key, right? These are fields that their intention is to reference a primary key. Okay, and so they can only reference other fields that have been declared to be primary keys. Okay, and it's just another type of constraint. It says that particular field, the values in that particular field, the only possible values that you could put in there are from other fields, right, that have been declared as primary keys, right? And then it relates, it bonds the primary key with the foreign key, right? So that if you try to remove the record with the primary key, if there is somebody who's referencing it, right, the database is going to stop you and say, wait a minute, if you have a record with a primary key and you have a whole bunch of other records that are referencing that primary key, you try to remove the primary key, right? It's going to stop you and say, no, you can't do that. You're going to leave all these people orphans, right? All these records are referencing you. If I let you remove this, then all these people are going to just be dangling. Okay. Yeah, so we already saw several examples of foreign keys like major ID, department ID, and whatnot, right? And so so here's an example of creating a department ID that's going to have a primary key, the department ID that we saw earlier. And now we're going to have an example of the foreign keys. Here's our student table, that has a primary key right here. Student ID is a primary key right there. Is being declared as primary key right there. See that? That's our primary key. And here's a foreign key. This is a field that's just a plain old integer. There's nothing special about it. We're saying that this is an ID. It's not a foreign key yet, not until we get to the bottom of this right here. See this foreign key? We're saying that the department ID field that is declared right here, right, is a foreign key, and it's going to reference this other table whose primary key is DID. See that? Okay. Now notice that we could have just declared the department ID, and department name without the primary key. Okay. And we could have also just declare the student with SID, student name, department ID, graduation year, and that's it. Left it at that, right? If we could have, without the primary key and the foreign key, just remove that, forget about that, right? I could have we could have mostly done everything we might want to do. I could have inserted a student, I could have inserted a department, I could have and created all my relationships, and the department IDs was an actual value of some department that actually existed. Yes, right? And the database would have let me do this just fine, right? And somebody might say, well, what do I even need primary keys and foreign keys for? Okay, and so but when you start doing things such as Oh, here I have all my 10 students that are in the chemistry department, right? And then I remove the chemistry department. Now my 10 students are orphans, right? They're pointing to a department that doesn't exist anymore. Yes, you might have said, it would have been nice if the database would have stopped me from doing that, right? Of now leaving all this data that's dangling, right? And that it would be nice for some validation, right? And that's where declaring things as primary keys and foreign keys come in. You want the database to enforce certain constraints, yes? Right, just like, for instance, say you have a directory structure where you have a directory has a whole bunch of files in there, yes? Right, and you inadvertently ask to remove that directory. What the operating system is going to stop you. It's going to say, you can't do that. That folder is full of other files. Yes, right, and it stopped you, and it, rightly so, it stopped you. Good thing that it stopped you, right? You would have blown away, a whole bunch of stuff. Yes, so same thing here, right? If there is a one-to-many relationship, one department has many students. Well, if I remove the department, I would like the database to stop me, because what's going to happen to all the students? So that's called referential integrity, right? The database is enforcing referential integrity. Make sense? Right? If you have the students referencing a whole bunch of departments, you cannot remove the department until you remove all the students. Make sense? And that's why we declare foreign keys and primary keys. We want the database to validate these things for us, right? And stop us if we do something stupid. Yeah. Schemas. So throughout the semester, I'm going to use a specific nomenclature in here in the slides and also in quizzes, right? Where you might see you might see me use a for the primary keys. You might see me do something like all bolded and or italic or underline, right? And so, for instance, for foreign keys, I'll use something like italic, right? And for primary keys, I'll use bold and underline, okay? And or from time to time, to make it even more obvious, I'll sometimes put a parentheses and say this is a primary key, and I'll say that this is a foreign key, FK or PK, right? You might see that in either slides or even in the quizzes, and so that it's obvious that this is a primary key and that's a foreign key. Yes. Okay. So just a nomenclature on how we're gonna talking about these things. Yeah, keys and primary keys and foreign keys allow us to relate students and departments in both ways, right? You can navigate from one to the other just by following from a foreign key to a primary key. Referential integrity, meaning I mentioned earlier, right, that the database is going to stop you if you're going to inadvertently leave records dangling, right? It won't let you do that. So, for instance, if you have a whole bunch of students, Amy and Sue, that both are in the major math department, right? If I try to remove the math department, it'll stop me. Okay? It'll stop me from that because I have records that are referencing that other record, right? Sorry. Or I might choose a couple cases. What I might say, the default is that it stops me, right? That if I remove the department, it's not gonna let me remove it because there are records that are already referencing it. Yes, that's the default behavior. Or I can configure a couple other things. How about, for instance, Cascade? I can say that whatever happens to the parent's record cascades down to the children's. Okay, right. So if I delete the parent record, that's going to cascade down to delete the child records, which here makes no sense, right? Makes no sense that if I remove the math department, well, I'm also going to remove all the student records. That makes no sense. Yes. Okay. Other things that I could do is that I'm just going to allow it. I'm going to say that if I remove it, well, that's fine. These guys are just left dangling. I might just leave it like that. Yes. Or I might say that if I remove this, right, the parent, then the children become null. But these foreign keys just become null, meaning they're not pointing anywhere, right? Or I might say that if I remove this, the 20 becomes something else, right? You know, if you were in the math department, then you're just going to be now in the computer science department, right? You were just moved from one department to another department. Yes. So we could set up different behaviors of what to do. Now this is called if I act on a parent that propagates to the children, we call that cascade actions. Okay, and the default like for instance, what I did here is that the foreign key, the way I configured it, right, was that the delete cascades. If you delete, it's going to cascade down to this record. If you update it, it also cascades. So if I change from 20, I change it to 21, well, that's going to cascade down to all the students. So if the department ID used to be 20 and now it's 21, well, then the student also are going to update also to be 21. Yes. Okay. And this is how you configure. You know, on delete you cascade, on update you cascade. You can say cascade. You can say null. You can say no action. Okay. Yes. Yeah, I think the default is no action, meaning don't allow it, don't allow it to go through. Yeah. Referential integrity below cascade actions. Other constraints, you could say that things can be null, right? Or you could say maybe not null, right? And that's how you say that a field is required or not, right? If you put a null next to it, the field declaration, then that means that it's optional, right? If you can leave it blank, right? But if you say not null, it means it's required, right? You have to provide a value. Key constraints with its primary or foreign key, referential integrity constraints. So constraints in general are for validating the value that you're putting in there. Creating tables, on cascade deletes, to-dos, primary keys, table students, creating a student table. Okay, I did this already. Oh yeah, so there's also checks, right? You can put all sorts of other validation rules, right? These foreign keys is so that make sure that if you delete the parent, the child is not deleted as well. But you can also put other validations such as verify that the IDs are positive, right? Or verify that the graduation year, right, it's greater than some value, right? Make sure that it's after the foundation of the school. You can't graduate before the foundation of the school. It makes no sense, right? So you can do all sorts of validations. You can also put all sorts of pattern recognition, right? That that emails have to have an @ sign, right? And have to have a domain name, or a zip code has to have 5 digits dash 5 digits. So you can put all sorts of validation, right, to make sure that the data you're inserting is correct. Yeah. So some of the typical constraints is not null, meaning it's required, that it's unique. Primary key, foreign key, default. Yeah. So not null means that it's required. You have to give me a value for this record. Now, in MySQL and SQL Server, some databases are slightly different, and so these constraints might be slightly different the way you write it for that particular vendor. In SQL, you could declare a field to be unique, right, by using the keyword unique. For instance, if something is primary, a primary key already sets that constraint on that field. Primary keys already says this field has to be unique, right? But you can also use unique on something that is not the primary key, right? Maybe you have a primary key, your student ID, yes, but you might say you have an email, right, as part of your profile, yes. Well, even though it might not be part of your primary key, you might want to make a constraint that the email has to be unique. It makes no sense that two people have the same email, yes. right? So you know, even though the email is not your primary key, you might still want to make sure that it's unique across multiple users, right? So unique allows you to do that. In SQL Server and Oracle, the syntax is slightly different. You put unique right next to the field, right, as opposed to as a separate line, right? So again, in whatever database you're actually going to be using, make sure you read the documentation. You can combine multiple fields, right, and give them. You can say that the combination of these two fields has to be unique, right? Yes.
So putting them in parentheses is the combination.
Yeah, exactly. Just primary keys as well. You can also put parentheses and field, comma, field, comma, field, any number. So we say that it's a compound relationship. Yep.
The other one you have to curly brackets.
Oh, that was when I was using the when I was writing it by hand. That wasn't SQL. Yeah, that was not SQL. Primary key, just primary key, and then this can also put comma and numbers of fields there. This is SQL. This is MySQL. And SQL Server is slightly different, right? You put it next to the field as opposed to a separate line, right? So again, the different vendors have slightly different syntax. Right, if you have multiple keys, right, you can put them in parentheses and list all the fields that make up the primary key. Foreign keys, right, is using the keyword foreign key, the field that you're saying that is referencing somebody else, and then the table that is being referenced, right, and the primary key of the other table, right? SQL Server is slightly different. You can give the primary key or foreign key, you can give them names by naming the constraint. You can say this is not required, right? But it's useful, right? That you can give it a name. You can say the constraint is called, you know, FK foreign key per orders, right? And then you can list the actual foreign key. So this is not needed, right? It's optional, but it's useful because things that are named, right, can be altered later, can be modified, right? There's a command called alter that you know, if you misspelled something, or you want to change the data type, or you want to change the table that it's being referenced, or you want to change the field that is being referenced, right? There's a command called alter that allows you to alter different parts of the schema, right? But you can only alter it if it has a name. If there's no name, you can't alter it. Okay, it's a pain, right? And another thing about these names have to be unique across the entire database. These names have to be unique. Oftentimes, it's a pain having to come up with these unique names. So you'll find a lot. A database will generate for you a random name, right, by default, right, and which has no meaning. So you might want to go and change it to something that's meaningful to you. But just remember that's unique. It's unique. You know, I'm sure I'm going to get a lot of Piazza questions. I can't create this. Give me an error. Blah blah blah. It's, you know, it happens a lot. It says, oh, your constraint has the same name as some other constraint. Yes. Yeah, no, you would leave out the whole thing. Yeah, you could just say foreign key with no name on it, right? But I think in the assignments, I do ask you to use a specific name, right, and just make sure that it is unique. Multi-fields, you could have multiple references, multiple foreign keys pointing to multiple primary keys. So here's a, you know, saying that two fields are referencing these two other primary keys in some other table, right? Some other table. Yep. Default allows you to specify a default value for a field, right? So I'm saying that the default value for that city is low, right? Same thing for integers or booleans or float, right? You can also specify the default. For dates, you can specify to get the current date, right? And then to initialize a value. So for instance, for instance, it's very common that we add a field to all our records called something like created, okay? So that when the record was created, yes, when it was first created, inserted into a database, and then you can have. It's also very common that you have a field called updated, right? And that update. So for audit purposes, it's great to keep track of when was the last time this record was updated, right? So for both cases, you can use the function getDate, right, which gets the current date, system date, to update a particular field. Auto increment we used last week, right, for auto choosing the value of our primary key, especially if you declare it as int, right? It'll start at 1 and then 2, 3, 4, 5. Some other vendors might use a different increment. So they might start at 10, then 20, 30, 40, right? So different vendors do it slightly different. You can configure that. You can give it a start, and you can give it an increment, right, to go on, so to go on further. A SQL Server is slightly different. You don't use the auto increment keyword. Instead, you use identity. Again, make sure to read the instruction for the particular vendor that you're using. So auto increment, if you're using auto increments, then you can insert, right? You can insert a new record, right? You can leave out the field, the ID field. You can leave it out, and the database will create the value for you, right? Or you can provide the value, and then it'll use that value, but you have to make sure it's unique, right? Make sure that it's not trampling on an ID that already exists. Otherwise, the database will stop you, right? You're using an ID that already exists. Okay, and so we'll talk about a little more when we talk about inserting data into the database. In Oracle, there's no such thing as an auto increment, right? Yes.
So is there any way where say add one record and auto
Yep.
you add another one so it's 2, then add another one so it's 3.
Yep.
And remove the one with the priority of 2.
Yep.
Build the auto adjust the auto even 3.
No, it'll keep the original values that it came up with. So it will not re-update. So you'll just be missing a 2, which you can use if you want yourself, right? Insert a record that has the 2, right? It's free. It's available, and you can even skip if you want, right? It'll always make sure that it's unique. So if you say you insert 10, 20, and 30, it'll do 1, 2, 3, get to 9, let's skip up to 11, and keep going. Oracle doesn't even have auto increment. They have instead an equivalent that is called a sequence, right? It's a dedicated, sort of like a table, where they fill up a really huge number of unique identifiers. Okay, and for instance, they might create as an integer that goes from 1 to 1,000,000, right? And then whenever you insert into that record, to kind of have the same feature as auto increment, you say, well, give me the next number in the sequence, right? So it pulls out the next value from that sequence, and it uses that to then insert the record. It's kind of messed up that Oracle doesn't have that. Yeah, so you create the sequence, it does the increment, and whatnot. Okay. All right. So how are we doing? A couple more minutes. Okay, let's get started with functional dependencies. This is a little bit theoretical, slightly theoretical. But the gist of it, I think you should be able to follow the gist of it. So one of the things that we want to do, again, we're going to repeat this over and over, right? We want to make sure we have no redundancy, right? Because we said, redundancy breeds inconsistency. Yes. And so what we're looking to, one of the ways to guarantee that there's no redundancy is by looking for functional dependencies. Functional dependencies, and the gist of it is that you want to look at in a record. You want to look at the fields in a record and see if there's any dependency of one field is dependent on another field. Meaning, does the value of a field of one of the record or one of the fields in the records, right? Does it give you any hint on the value of some other field, right? For instance, if I had two fields, one is a car model and the other one is brand, yes? And I told, and these are two fields in the same record, yes? And I tell you that in the record, for the field car model, I say Corolla, right? So what would you expect for me to put in the brand, right? It could only possibly be a Toyota, yes? So we say that there's a dependency between those two fields, right? That one of the fields is kind of giving you a hint on what the other value is. So there's a functional dependency between the two fields, right? So we're going to be looking for these things, right? Now, and we're going to try and eliminate those functional dependencies, right? Because what we would like to be able to do is, if you're going to have those two fields, can we somehow guarantee that you're not going to give me garbage for those two fields? That you're not going to say model Corolla, but then for the brand, you're going to give me a Ford, right? It just makes no sense, right? So if we can guarantee that you're not going to give me garbage, then it's okay. Leave the two fields together. But if there's no way for me to guarantee that you're not, I can't stop you from giving me garbage, then you should not have the two fields together. Make sense? Okay. So functional dependencies is a way of trying to find redundancy, right? We're trying to stop you from creating fields that go together that should not go together, right? So functional dependency is the fact of identifying these special cases where things should not be together and should actually be split. So a better implementation is that having the model and the brand not be in the same table, but instead, usually it entails splitting it up and say, well, no, then there should be a separate table that has all the brands, okay, right? And another one has all the models. And then there's a one-to-many relationship so that you know these are all the models for a particular brand. Right now, with the foreign keys and primary keys, now we can guarantee, right, that only certain combinations are valid, and many of them are not. Make sense? So functional dependency is the notion of trying to identify what the dependencies are, seeing if it's an okay dependency, right, and whether we leave it or not, right? So yeah, why don't you read functional dependencies, and we'll catch this up when we come on Friday, right? It's a little dense. So I'd rather you read up on it, and then we can discuss it in class. All right, excellent. Thank you. Bye, everybody. Five 30.
Okay. Thank you. So I just have some questions. I can you guys like did the UML diagram correctly, but just implementing it.
Yeah, so we can take a look. Yeah, we can take a look. Take care. Yeah, I just need to get out of here for the next stuff.
Super tight.
Yeah, well, I'll be right out.